Right. Yeah, that's a non-trivial part. So in the case of
the last talk of the day, Nick will tell us about hot radiation of lattice.
But if there is a fundamental matter, the surface becomes non-topological.
All right. Well, first of all, thanks to the organizers, of course, for giving me the opportunity to speak here. It's my first time in Durham, and I think it's a very nice city, and also the conference has been very interesting so far. So today I will be talking about Hawking radiation. You know, the project I will be talking about was really, the goal of it was really to construct the simplest UV complete model that we could write down that exhibits Hawking radiation. And I think one reason for the motivation for this, and one reason why I think this is a useful exercise, is that you can look at the original calculation of Hawking, and it's very beautiful, and arguably, you know, perhaps one of the most influential calculations in theoretical physics of the previous century. But still, if you look at the calculation, several aspects remain mysterious, at least to me. Maybe some people have a deeper understanding of, about this. But, you know, simple questions like, where do these particles now come from? Does stuff actually escape from behind the horizon? What's going on? Exactly, these simple questions are not really answered by this calculation. And I think this is in part also because we don't have actually a very adequate, simple physical picture of what's going on. Like exactly what is the physics, like why do we get thermal radiation, where is it coming from? Okay, so the outline of my talk is as follows. So I will start by first actually discussing the continuum calculation. So I will discuss Unruh Hawking radiation for 1 + 1 dBr fermion in the continuum. After that, I will introduce a lattice model, will be a Floquet model, but well, for people who don't know what a Floquet model is, I will define it once I get there. I will argue that this model has a supercausal horizon. And then the final part of my talk, I will show that indeed this lattice model reproduces the features of Hawking radiation that we find in the continuum calculation. Also, before I proceed, so as I said, our aim was to construct a simple model. So if at some point during the talk you don't feel that what I'm saying is simple or borderline trivial, please stop me, because it means I'm not explaining it well, okay? So, first, Unruh Hawking radiation for 1 + 1 dBr fermion. So let's start by just defining our Minkowski Hamiltonian, right? So this is the Minkowski, this is the Hamiltonian flat space, and like I said, it's 1 + 1 dBr fermion. And so I've written it in terms of the two wild fermions, the two chiral fermions. So I have the right moving fermion and the left moving fermion, and v is the velocity of these two wild fermions. Actually, and for this talk, we can completely ignore the left moving fermion because it's just a spectator for the Hawking effect. So from now on, I will only write psi, and this is really the right moving fermion. So this is now my simplified Minkowski Hamiltonian, and if we imagine we can define a proper ground state for it, then it's simply Fil-Dioxy of all the negative momentum states. Okay, so then we need to now, the way you get Hawking radiation is to quench this vacuum state, to time evolve it with a state, a Hamiltonian, which has a horizon. So what is the simplest picture for a horizon? Well, you just, this is famous picture in terms of these light cones. So these lines here just represent light cones. Far away on the right, we have the light cones of Minkowski, and as you approach the horizon, which is this dashed line here, your light cones start tipping, they start tilting, and at some point they completely tip over. And here on the left, you're forced to move closer to the origin, or you're forced to move away from the horizon. So once you're here, you're trapped, and there's no, without violating causality, you can never really escape this region anymore. So put differently, on the right or on the outside of the horizon, you can move both to the right and to the left. Once you're stuck behind the horizon, you're forced to move to the left. So here we have a left and a right mover. Here we have two left movers. And really, the Hawking effect is entirely due to this mode, which changes its chirality upon crossing the horizon. So this mode here, which is left moving everywhere, this mode is also, this is the same mode as in the Minkowski Hamiltonian. So this is a spectator, and we ignore it. So we want to write down a Hamiltonian for this mode, which changes chirality, and it's very simple. It's a very easy generalization of the Hamiltonian for Minkowski Hamiltonian. We just have to now make this velocity spatially dependent. We can do that at the price of introducing this additional term, which is necessary to ensure that the Hamiltonian is Hermitian. And of course, we want this velocity function to satisfy the following two properties. It has to be positive here on the right, so that you're moving to the right, and it has to be negative here, so that you're moving to the right. And there's two interesting choices for this v of x, this velocity. You can simply take it to be proportional to x with some kappa. Kappa is dimensional constant. It has dimension 1 over time, or since we're working in units where h bar is 1 energy. And this, if you make this choice, then you have a Unruh Hamiltonian. And the way to see that, you can just look at the Rindler metric. It takes this form, so this is your velocity here. So if you put this equal to 0, then you get the velocity of your massless particles, and it's exactly this kappa times x.
Can I ask a question?
Yeah, sure.
You started with a Dirac fermion, which had a right mover and a left mover.
That's right.
And then you threw away, say, the left mover.
That's right.
And then you made the right mover left moving and right.
Exactly. That's it. Yes, yes, that's it. Yeah, no. Good. Borderline trivial, as I said. They're gonna, yeah. Okay. Yeah. No, if you, no.
It just seems a bit odd. And I'm worried in particular that when you go to the lattice, it's hard to throw away a right.
No, exactly. Yeah, no, exactly.
Yeah.
This is all motivation. Yeah, no, exactly. We'll have to do some trickery on the lattice. Yeah. Yeah, definitely.
Sorry, why does the energy go with the horizon?
Sorry, what?
You usually, if you have a parallel mode, you cannot reverse it, right? It's just
Well, this is a well-defined Hamiltonian, I would say. And this is, you could take the Dirac Hamiltonian, introduce a Vielbein spin connection, put it in a Schwarzschild metric, and then at the very end you get something like this. I mean, this is a well-defined Hamiltonian. Yeah, in terms of, I mean, yeah, what energy? This is, of course, all. Yeah, I don't know. What do you mean? Where does the energy go?
Can you do the previous slide?
This one? No.
Oh, yeah, yeah. So you said you were throwing out one kinetic,
Yes.
but here you're showing both.
Well, yeah, but this is just, yeah, no, this is right. But again, I'm keeping only the one in the red box.
So
This
he's
one I'm
changing
not
the
gonna be-
velocity of that one mode and half the space and another half, so it's right mover on the right, but it's a left mover on the left.
Okay, so, right.
The extra piece is kind of like a local chemical potential.
Yeah, only it's imaginary. So it by itself would not give you Hermitian Hamiltonian, but the combination of the two terms is Hermitian. So it has no equivalent without having this velocity dependent, especially dependent velocity. All right, so that was the Unruh case, which is this. The Hawking case you can get by plugging in this hyperbolic tangent. Precise functional form doesn't matter. The only thing that matters is that it's linear. It's like it has a linear term near where x is 0, and if x goes to infinity to plus infinity, this just becomes constant. So this means that at spatial infinity, you asymptote to Minkowski space. So the boundary condition of Schwarzschilds over black hole space that's very far away from the horizon should be in Minkowski space. Right, so this is the only technical slide. So for this general Hamiltonian, you can actually write down, you can exactly solve for all the single particle wave functions. You can write them down in a closed form. They have this form. Doesn't matter, the details don't matter. I just want to show that you can do it. And for every single particle energy omega, you find two degenerate eigen. You find two solutions, so there's two eigenstates. And this is the plus and minus combination here. But I can also just take a different linear combination of these two states, and by doing that, I can also just have a solution which is supported entirely on the inside, and a degenerate solution which is supported entirely on the outside. If you now take a solution and you plug in the Unruh velocity profile, you recover by a very simple calculation, actually, the famous Unruh result. So you find that the occupation of the outside modes is exactly given by this thermal distribution, so the Fermi-Dirac distribution, And this is, of course, a famous Unruh result. So to an accelerating observer, the vacuum looks like a thermal density matrix after you trace out all the stuff that's behind the horizon. Also note that from this calculation, it's very clear that the Minkowski vacuum is a stationary state of the Unruh Hamiltonian. So if you would time evolve the Minkowski vacuum with the Unruh Hamiltonian, you wouldn't have any trivial, would only have trivial dynamics, actually no dynamics. Now if I plug in this, the Hawking velocity profiles as this hyperbolic tangents, then I will have non-trivial dynamics if I time evolve my vacuum with this Hamiltonian. And the physical picture is as follows. So far away plus infinity, I imagine Minkowski Hamiltonian. So here I'm at zero temperature, I'm in the ground state. Then here, very close to the horizon, you can approximate your Hawking Hamiltonian with the Unruh Hamiltonian. And so locally you see this Minkowski vacuum as a thermal path at some temperature T, which is cut over 2 pi. And what will happen during the quench or the time evolution is that particles will be emitted from the hot region to the cold region. And this is the Hawking radiation. And the origin of these particles is really this region here where we have curvature and velocity. Because here, as I told you, like for the Unruh Hamiltonian, Minkowski vacuum is a stationary state. Of course, here we're also in stationary states. Only so the dynamics all comes from this region where you have some curvature in velocity.
Could I have a question? I mean, is the vacuum that you're taking in all of this, the state, the ground state of the Hamiltonian with V constant?
That's right.
Okay.
That's right. So that the idea also in Hawking's calculation is at minus infinity, time minus, you start with a vacuum of the Minkowski state. Space, yeah.
Well, again, what I'm used to is that you have for an infalling observer, they see nothing strange, which is not obviously the same, I think, but I guess you're saying it is at the end of the day the same.
Right, so this Hamiltonian here, it's time evolving like the Schwarzschild time coordinate, right? Far away, it's really just evolving so this is really the Hamiltonian which would describe time evolution for a stationary observer far away from the horizon. Good. And so this is the picture, and also something interesting to note is that actually behind the horizon, the Minkowski vacuum is actually the highest energy state. It's like temperature minus epsilon, that's 0 minus. And then actually this would be a cold region, and okay, not going into details. Okay, now the lattice model. So now we want to mimic this behavior on the lattice, and it was already pointed out that it's not going to be so trivial because, well, okay, first we have to, what is trivial is defining, lattice version of our Minkowski Hamiltonian. It's the most trivial Hamiltonian you can write down. It's just fermions hopping on a 1D chain indexed to its size indexed by this integer j. And so they're hopping back and forth with this hopping strength t, and also added these phases, hopping phase I and minus I. That's just to have a single particle dispersion, which is a sign where I have this zero energy mode at zero momentum. It's not crucial, it's just, I don't know, useful, I think. Right, and so I have filling, my ground state is just obtained by filling all negative momentum states, a right mover at momentum 0, left mover at momentum pi, and the velocity of these modes is plus minus lattice constant times this hopping strength. That's now my ground state, and now I want to quench it. I want to time evolve it with a Hamiltonian which has a horizon, but yeah, as was pointed out, we have this problem because here we have a chiral region. And so of course, we cannot write down a 1D local Hamiltonian which is chiral, so we need to do something else to get around this. And one way around this obstruction is to discretize a time evolution. I actually study a stroboscopic or Floquet time evolution, which means that we're actually going to evolve our state in discrete steps. So our time evolved state is defined by applying this unitary u delta t n times on our vacuum. And this unitary here is called the Floquet unitary. It's a product of two operators. So the first product here is just simple conventional time evolution with a local Hamiltonian. This is the local Hamiltonian. It's almost the same as my Minkowski Hamiltonian, only now the hopping strengths are spatially dependent. And then the second unitary is just translating to the left. So an operator at side j gets translated to an operator at side j minus 1. And so with this Floquet unitary, you can define an intrinsic Floquet velocity, which is simply the lattice constant divided by your time, like the length of a single Floquet step.
So this is moving the lattice in time, is it?
this translation.
Yeah.
Um,
It's both involving the Hamiltonian and
that's right.
moving the lattice.
That's right. That's
Why
right.
do you need spatially dependent feature?
I'll explain. Yeah, yeah. Because we have special points, we have horizons. It's not a uniform system, but yeah. So yeah, these TJs are defined as follows. So we just define the TJs as via some continuous function t of x and evaluate it at discrete points and multiples of the lattice constant. Of course, I'm doing a translation in every step, so I have to either work with an infinite system or a system with periodic boundary conditions, and I chose to work with a system with periodic boundary conditions. So, and this t of x is a periodic function, so n is the number of lattice sides, and so if you shift by n times the lattice constant, you get the same, the t is invariant. And I then make a choice for this t of x such that the associated velocity profile, which is a lattice constant times its hopping strength, is larger than the Floquet velocity in this region, where this dashed line here is what I call a special location, which I call xb, and this other dashed line here is a location which I call xw. And so between these two, my velocity function is larger than the Floquet velocity, and here the velocity is smaller than the Floquet velocity. And I claim that with this choice, you realize a situation where your Floquet unitary has the following dynamics. So there's in this region where the velocity is larger than the Floquet velocity, you can move both right and left. Whereas if your velocity is smaller than the Floquet velocity, then you're forced to go to the left. And so this really means that this xb, this is really my black hole horizon, because once I'm here, I'm forced to move to the left, and I cannot really cross this boundary in this direction from left to right. But I also have to introduce additional white hole horizon, where now the white hole horizon is a special point from which I can only escape the region behind the horizon. I cannot enter this region in this way. How can you see that this is now really what's going on or what's happening? Well, it's very simple. So during this first time evolution, a particle that's here can move, or a particle that's anywhere actually, can move to the right over a distance which is Vx times delta t. And then after this evolution translate to the left. So if this displacement is smaller than the lattice constant, then over the entire Floquet time step, there will be net displacement to the left. And this is true exactly when this condition is met. So here everything has to move to the left, here you can move left and right. Okay, so that's the model. And now I just have to show that it indeed gives Hawking radiation.
Is it non-interacting?
It's all non-interacting, yeah.
So we will
Simple
go-
waves and wave phenomena, yeah. Yeah. But the original Hawking calculation is traditionally done also with a free scalar field. It's all free. I mean, there's very little work on Hawking radiation for interacting theories. And the hope is that maybe this simple picture would allow you to maybe do Hawking radiation for an interacting system, maybe numerically, but. Right, so how do we detect the Hawking radiation? We define wave packet creation operators, as W daggers. So x0 is the position, the spatial position of the wave packet, omega is the energy, and omega is related to momentum in this way, where this is the net velocity, this is the velocity from our Hamiltonian minus the Floquet velocity. And I make these wave packets with momenta, so these are superpositions of plane waves with small momenta, so momenta near zero. And the width, of course, when you define a wave packet, you have to define a width, but it doesn't matter. As long as the wave packet in space fits between the black and white hole horizon, it's fine. The width doesn't matter too much. And then what you do is you simply calculate the occupation number of these wave packets at some position x0 and for some energy in the time evolved state. And again, I remind you, we actually do this in discrete steps, right, with this Floquet unitary. And if you do this and you take x0 to be far outside the black hole and you wait long enough, then you see that the occupation of these wave packets indeed, so these blue dots are just numerical data points, and the full blue line is just the Fermi-Dirac distribution, again at the Hawking temperature kappa over 2 pi, where in this lattice model kappa is defined similarly as in the continuum model. It's just the slope of the linear part of this function near the horizon. And so you find indeed, it's actually remarkable how accurate this is. Like this agrees remarkably well with the continuum calculation. And we also have these red points, and these are the points on the inside of the horizon. So there, if you wait long enough and you calculate the wave packet occupation number on the inside of the horizon, you find it actually from the dark distribution but with a negative Hawking temperature.
Could you show the formula for kappa again in terms of? Could you explain the motivation for that formula, the one defining kappa? Is that an empirical observation, or is there a way to?
It's the one which matches the way kappa is defined in the original calculation by Hawking continuum.
I see.
Yeah.
I see. It's like DVD. It's like DVDX.
Exactly. Exactly. Yes. Yes.
Thank you.
Okay, so this is what you can easily calculate. This is all, again, more or less trivial numerics. You can also calculate wave packet correlations across the horizon. So you can annihilate the wave packet at some position x out on the outside and create one at x in on the inside. And this maximization here is really you fix, for example, the inside location and then you maximize on the outside location. And then if you plot this correlation function of the wave packets as a function of their energy, you find that they lie nicely on top of this blue curve here, and the blue curve is now square root of the Fermi Dirac distribution at the Hawking temperature times the Fermi Dirac distribution at the negative Hawking temperature. So this shows that really during this quench process, during the time evolution, you're emitting indeed like correlated pairs of particles. And this is further exemplified by calculating the entanglement entropy. So this is a lattice model. We can calculate an entanglement entropy which is finite. And you can see that the entanglement entropy across the horizon, the entanglement across the horizon grows grows perfectly linear during the time evolution, so during the quench.
So the initial state is the ground state.
Exactly, yeah. Yeah.
And then you set up with spatially.
Exactly.
When you start evolving it.
Exactly, yes, yes. So this is really, like, in kinematic, I've used this word quench a couple of times. I don't know how common it is in the high energy literature, but this is really like, people have been studying quenches and CFTs and I guess in high energy as well, but this is a standard protocol and it's a standard thing to study dynamics. And also there, like Cardi collaboration found that a very generic feature in CFTs, if you quench them, is you get this linear growth of entanglement entropy, and it's also reproduced in this model.
Does it stop at certain time?
Yeah, no, it will saturate at some point. Yeah.
But your system does not heat up the temperature because there are no interactions.
That's, well, in some sense it does, but it's only like the left. It doesn't actually thermalize because it's only, you see if outgoing flux, like the inwards moving modes are still in the ground state for some reason. So it never reaches an equilibrium state. I don't know if that made sense, but I mean, really, because I have a black and white hole horizon, my system will only mimic the Hawking calculation for some finite time, because at some point, you know, quanta start escaping through the white hole, bounce of the white hole, and then, you know, stuff starts to deviate from the Hawking calculation. So there's actually no equilibration here. Yeah. It's a constant dynamical process. Okay, and you know, so I haven't addressed my original question, the motivating question, like how can we now understand this? Because this is just showing a lattice model can reproduce a continuum calculation, but can we now use it to understand the origin of the Hawking particles? Where does this flux of particles come from? And it's actually, there's a very nice way to see it. And what you do is you just calculate the single particle Floquet dispersion relations. So you just find some eigenvectors, find some linear combination of these Fermi creation operators, which are just stationary. You just acquire a phase under the Floquet time evolution. And we're actually going to do this for the case where now I do take a homogeneous Hamiltonian, translation invariant Hamiltonian, because then I can just calculate a dispersion relation. This omegas can now if the k is a quantum number, then I can write omega as a function of my momentum. And this Floquet dispersion is basically just again this sign but now minus k times the Floquet velocity. And so if I plug in a value for v or t corresponding to this region where it's larger than where v would be larger than Floquet velocity, I get this type of Floquet dispersions. Notice it's actually continuous because of the discrete time evolution, energies are only defined not 2 pi over delta t, so this is actually continuous. And so here near zero momentum I get this right mover, and then if I use a value for v which corresponds to the inside region, where v is smaller than my Floquet velocity, I get this, and now my mode near zero momentum is left moving. But one striking thing is that we also have this additional mode here on the outside. So this is a left moving mode. We also have this one, but this one isn't important. Only this one is important because recall that in the vacuum, in the ground state of my uniform Hamiltonian, all these negative momentum modes are occupied. Right? So this is basically my Fermi sea here. So this branch here is entirely occupied, which means I have a left moving branch which is occupied, and so this will constantly give plane waves moving towards the horizon during the time evolution. And it's a simple scattering process because these waves will move towards the horizon, and suddenly there's this object, this is the horizon, and they will scatter off this horizon. So basically, this is the incoming wave, and then there will be two parts of the outgoing waves. So part of the wave will scatter to this branch here, which is the outgoing branch, and this then will be observed as a Hawking particle, and another part of it will just go through the horizon. And you can actually make a wave packet and just see this behavior. So this is incoming wave, the dashed line is the horizon, it scatters off, and then part of it moves through, and another part is reflected back. So these are fermions which are deep inside the Fermi sea of my vacuum. And but once it scatters off this horizon, it emerges as a Hawking particle, which is now moving out. And you can easily calculate the transmission and reflection coefficients for these waves. And indeed, as you would expect, the transmission coefficient is the Fermi-Dirac distribution at the negative Hawking temperature, and the reflection coefficient is the Fermi-Dirac distribution at the positive Hawking temperature. So really, these scattering processes, they explain all the numerically observed properties of Hawking radiation. They observe this flux of quanta coming out. They explain the correlations, because really these waves are in superposition of being inside and outside, so there's like entanglement and correlations. So all these things are explained by a simple physical picture. And one final interesting thing to note is that these wave packets never follow classically forbidden trajectories. So this picture is really fundamentally different from a tunneling picture, where you would have a wave packet which has a small probability to do something which is classically forbidden. But that's not what's going on here. Like, all these trajectories are allowed. They're classically allowed. Okay, so that was the story. So this work was together with Kyle and Dan, and Kyle actually was here in Durham a long time ago, 2004 to 2006. I don't know if anybody still here that overlapped with him. So this is the paper, and I said in my abstract there were two models I was going to introduce. There's an additional lattice model, which is in the paper, and that one is strictly local. It is just time evolution with a local Hamiltonian, so no translating of the lattice. But that one is not able to realize a strict causal horizon, but nevertheless, even without a strict causal horizon, you can still have Hawking radiation. But yeah, I didn't have time to talk about that. So if you're interested, we can look at the paper. Okay, thank you.
Any more questions?
I have one, but I asked several, so. Okay. It's amazing that you get exactly the Fermi-Dirac distribution for all values of delta t. Is that correct?
No. So I mean, once my velocity profile starts varying faster than the lattice scale, then obviously you're going to have very different results. No, I mean, you have to choose kappa. Kappa is basically the slope. It's like saying how fast your velocity profile is changing.
Right.
That has to be larger than the lattice constant.
Sure.
So
Within that regime, it still seems amazing that you get.
Yeah, and also because the way you get actually the particle is completely different. Like, you basically also just the points I want to something to think about is actually the continuum Hamiltonian. You can actually think about as being Hamiltonian on the left plus a Hamiltonian on the right, which are actually completely decoupled. So it actually doesn't generate any entanglement. So really what's happening is a continuum. You just started with the vacuum, which is an infinite path of entanglement, infinite path of correlated pairs, and just pulling them out of the vacuum, basically.
Right.
And that's completely different from what's happening on the lattice. You really have the waves coming in. So I think, yeah, it's remarkable that you reproduce the Hawking results but still the mechanism of how you get the Hawking radiation, I think is very different on lattice.
Do you have a sort of analytic reason why you got Fermi? Because the explanations I know for getting Fermi direct, as far as I can tell, none of them really apply here. They involve,
Yeah, that's right. That's right. Yeah.
Do you have an analytic understanding why you got Fermi direct distribution?
No, and we tried hard. We tried for the local Hamiltonian. You can actually just get these results without actually doing time evolution. You just construct stationary scattering states, and you know the amplitudes of the outgoing waves should encode the Hawking distribution. You can do it. We tried very hard to solve that problem analytically, but we couldn't. At this point, no, we don't have an analytical understanding. Maybe you can do some, approximation. It's just, I don't know, it's micronal approximation or something else but yeah, we didn't do that. No.
Can you also shrink the black hole while it evaporates? It's whether
Yeah.
big hole or something.
Yeah, I don't think that's. Yeah. There's no back reaction here. Like I don't know how to introduce that, and I mean, yeah, I don't know if you do that, whether that would really mimic an evaporating black hole. I'm not sure. Also, we also have this white hole horizon, but yeah, maybe I don't know. We could do it, but I don't know what it would tell you. Let me put it like that. Yeah.
Have you started to look at some interacting cases?
We did. Yeah, so the GAN group has a big group of DMRG, well, MPS people, and we're thinking of, doing this with a spin chain. It still requires, I would say, one conceptual step, which is because now it's no longer single particle physics. There's a non-trivial step of how actually now what's the analog of these wave packets operates. You have to have an operator in the interacting theory which creates a wave packet and that's it can be done, but it's still a non-trivial step you have to do. Yeah, but in the end, also the actual Schwarz, the actual Hawking calculation, it's all 1D physics in the end because you just work in S-wave basis. That's just everything's happening on radial direction. So it's actually intrinsically a 1D phenomenon, I would say.
All right. There's no more questions. Let's thank Nick again.